Good day po, sir. This is the presentation of my project. For this project, I created 5 Java programs and converted each one into MO8086 assembly language. These programs cover important programming concepts such as selection statements, loops, nested loops, procedures, and arrays. By translating this concept into assembly, I was able to see how each one works at the machine level. This project helped deepen my understanding of both high-level programming and low-level machine operations. So now, let's begin with the first program. Arithmetic operations and prime number checking. In this program, I first declare two integer variables, num1 and num2, and assign them the values 20 and 9. Then, I perform 4 basic arithmetic operations, which is the addition, subtraction, multiplication, and division. Each result is stored in a separate variable named sum, difference, product, and quotient. Next, I display the original values of the two numbers using system.out.println. After that, for each operation, I print the result followed by a call to a method named prime checking. This method checks whether the result is a prime number, which is an example of a selection statement being used, likely an if condition inside that method. Now, let's move on to the prime checking method, which is a void method used to check if a given result is a prime number. First, it checks if the number is less than or equal to 1. If it is, the program immediately prints that the number is not a prime number and exits the method using return. Next, if the number is greater than 1, we assume it is a prime by default using a Boolean variable named prime result, which is set to true. Then, we use a for loop to check if the number is divisible by any value from 2 up to half of the result. If it is divisible by any of these values, it's not prime, so we set prime result to false and exit the loop. Finally, based on the value of prime result, we print whether the number is a prime number or is not a prime number by the if-else selection statement. By running this program, this will show the two declared values for num1 and num2, which is 20 and 9 respectively. Then the addition result is 29, which is a prime number. Subtraction result is 11, a prime number also. Multiplication result is 180, which is not a prime number, and the division result is 2, which is a prime number. Now, this is the converted assembly language of my first Java program. Inside the data, I declared two variables, num1 which is equals to 20, and num2 which is equals to 9. These are the two input numbers. I also declared strings like first number, second number, and labels for each arithmetic result to be printed on screen. Next, in the code section, I loaded the data segment address into DS using moveax.data and moveDSAX. I started the output by printing first number using interrupt21h function 09h. Then I moved the value of num1 into register AL, cleared AH, and called the custom procedure print decimal to display the value numerically. After that, I printed second number using the same method, loading num2 and again calling print decimal. I also inserted new line characters using interrupt21h function 02h by passing ASCII code 13 and 10 in DL for carriage return and line feed. Now let's move on to the arithmetic operation. First, for the addition, the value of num1 is moved into register AL. Then we use the add instruction to add num2 to it. The result is stored in register AX and we copy it into the result variable. The program then loads the label addition result into DX and calls the print result procedure to display both the label and numeric result. For subtraction, similar to addition, we move num1 into AL, then subtract num2 using the sub instruction. The result is again stored in AX, moved to result, and printed by calling print result with the subtraction result label. For multiplication, num1 is loaded into AL and AH is cleared. Then we use the mul instruction to multiply it by num2. The result, which could be up to 16 bits, is stored in AX, then saved in result. As before, the result is printed with the multiplication result label. And for division, num1 is loaded into AL and AH is cleared to prepare for division. Using the div instruction, we divide by num2. The quotient is stored in AL, which ends up in AX and then in result. The label division result is printed, followed by the result. Each operation is followed by a call to the print result procedure, which handles the output in a clean and reusable way. Finally, the program uses interrupt21h function 4ch to safely exit back to the operating system. Now, let me explain the print result procedure. First, it uses interrupt21h function 09h to print the label such as addition result or division result. Then it moves the value stored in the result variable into register AX and calls another procedure named print decimal. This prints the actual numeric result in decimal format. After displaying the number, it calls the prime check procedure to determine and display whether the result is a prime number. Finally, the ret instruction returns control to the main program. For the print decimal procedure, this procedure converts the number in AX into individual ASCII digits so it can be displayed properly. It first pushes all used registers AX, BX, CX, and DX onto the stack to preserve their original values. It clears CX, which will be used to count how many digits the number has. For the divide digits, the procedure uses a loop to divide the number by 10 repeatedly. The remainder from each division, which represents a digit, is pushed onto the stack. The loop continues until the quotient becomes 0. For the loop print digits, once all digits are collected, the procedure enters another loop to pop each digit, convert it to its ASCII equivalent by adding 0, and print it using interrupt21h function 02h. After printing, the registers are popped off the stack to restore the original values, and the procedure ends with return. The prime check procedure determines if the value stored in the variable result is a prime number. First, the procedure pushes AX, BX, CX, and DX onto the stack to preserve their current values before any calculations are made. The value of result is moved into AX and then the lower byte is copied to CL since we use CL as our target number to check for primality. If the value is less than 2, the program jumps directly to not prime because any number less than 2 is not a prime number. Then we have the loop to check divisibility. The register BL is initialized to 2, which will act as a divisor in our loop. The check loop label marks the start of a loop that checks if CL is divisible by any number between 2 and itself minus 1. If BL is already greater than or equal to CL, then the number has no divisors and it jumps to is prime. Inside this loop, the value in CL is moved into AL, division is performed by BL, and the remainder is stored in AH. If the remainder is 0, it means the number is divisible by something other than 1 and itself, so it jumps to not prime. Otherwise, it increments BL and checks the next number. For printing the result, if the number is prime, the procedure jumps to the is prime label and prints the string is a prime number using interrupt21h. If the number is not prime, it jumps to the not prime label and prints it's not a prime number. At the end of prime label, it pops all the registers it used back from the stack and returns control to the calling procedure using return. By running this code, this will show us an output exactly like the output of the Java program, which is this. The second program is about finding common characters between words. First, I declared two long and unique words which is anti-disestablishmentarianism and supercalifragilisticexpialidocious. These two words are printed using simple system.out.println statements. Next, I call a custom void method called common characters, passing both strings as arguments. Inside the method, I initialize an empty string named common, which is used to store unique characters found in both words. I also convert the second word to lowercase to make sure that comparison between characters are case insensitive. Inside the common characters method, I use a for loop to go through each character in the first word. Each character is converted to lowercase to make comparison consistent. Before checking for matches, the program first makes sure that the character hasn't already been added to the common string so that it avoids duplicate entries and ensures only unique common characters are displayed. Then, another loop checks if the current character exists anywhere in the second word. If it does, the character is added to the common string. After scanning all characters, the program checks if any common characters were found. If not, it prints a message saying no common characters found. Otherwise, it prints all the unique characters that were common to both words. By running this program, the output will show the two declared string word, which is the anti-disestablishmentarianism and supercalifragilisticexpialidocious. Next, it prints the common characters based from the two declared word. And the found common characters are A, T, I, D, S, E, L, and R. Now, let's move on to the converted MO8086 assembly language of defining common characters between words. In data segment, word 1 and word 2 hold two long words, which is the anti-disestablishmentarianism and supercalifragilisticexpialidocious. The array common is initialized with 50 0 bytes. This will store any shared characters found. The message 1, message 2, and message 3 are message strings that will be shown to the user before each word and before the result. Next, in the code segment, the program begins by initializing the data segment using moveAX at data and moveDSAX. It then prints the first message, first word, and follows it with the content of word 1. Next, it prints the message for the second word and displays word 2. Then it prints the heading common characters. Now, we start scanning word 1 character by character. We load the address of word 1 into SI and begin a loop labeled check next char. The instruction load SB loads a byte from word 1 into AL. If the character is a $sign or a string terminator, it skips it. If it's 0, we reach the end and it jumps to show common. The reason why I put code wherein it skips the $sign or the string terminator is because if I don't, it will be included in the common characters result. Before any comparison, the character in AL is converted to lowercase by a custom to lower procedure, ensuring case-insensitive comparison. For the check duplicate, the program now checks if the character is already stored in the common array. DI points to the start of common, and it compares each byte to the current character in AL. If it's match, it means the character is already found earlier, so it skips it and returns to check the next character in word 1. If no match is found and it reaches 0, it proceeds to compare this character with characters in word 2. Next, the check in word 2 will scan the second word to see if these new characters exist there. If it does, it will be stored in common. After setting up the initial comparisons, the program moves into checking the characters of word 2. Next, word 2 char, this label starts a loop that goes through every character in word 2. It loads each character into register BL, and if it encounters the end of the string, marked by the string terminator symbol or a null byte 0, it either skips or ends the check. Every character is converted to lowercase using the lower BL procedure, so the comparison is case insensitive. Then it checks if the lowercase character in BL matches the lowercase character from word 1. The program jumps to add to common to save it. Inside add to common, the program first points to the common array, where it searches for the next available empty space using the label findEmpty. Once an empty slot is found, it stores the matching character using moveDIAL and null terminates the string with a 0 right after it. It then jumps back to the check next char to continue comparing the next character in word 1. When all characters have been checked, the program moves to the show common label, where it loads each character from the common array, print it using print char, and follows it with a space. The loop ends when it encounters a null terminator, and finally, the program exits using moveAH for CH and int21H. For the print string procedure, it simply displays a string on screen. It uses interrupt21H with function 09H, which prints characters starting from the address in DX until it hits the string terminator. Next, the print char procedure displays a single character stored in DL. It uses interrupt21H function 02H, which is specifically for printing one character. Now, we have the to lower procedure. This checks if the character in AL is an uppercase letter by comparing it between letter A and Z, and if it is, it adds 32 to convert it to lowercase. Similarly, the lower BL procedure does the same check, but for the character in BL register, it ensures both words are compared in lowercase, making the search case insensitive. By running this code, this will show us an output exactly like the output of the Java program, which is the common characters A, T, I, D, S, E, L, and R. For my third program, this is all about summing array values. First, I declare an array named numbers that holds 10 integers values, which are 115, 89, 205, 7, 310, 90, 160, 56, 186, and 67. Then, using an enhanced for loop, I print each element of the array to show the original contents. Next, I initialize a variable sum to 0. I use another loop to iterate through the array, adding each element to sum. Finally, I display the total sum of elements in the array. This will show an output that the sum of all numbers in array is 1285. Now, this is the converted MO886 assembly language of the third program. First, I define a 10-element array in the .data section. After initializing the data segment, the program displays the label original array. Then, it enters a loop to print each element of the array using a procedure called printNum. A space is added after each number for clarity. After printing the array, it moves to the next part, calculating the total sum. Using a second loop, each value in the array is added to a register holding the running total. Once the loop finishes, the label sum of all numbers in array is printed, followed by the actual computed sum. Then, the program exits cleanly using interrupt21H. Now, let me explain the procedure. This is the printNum procedure. This is used to convert and display a number stored in the AX register. It begins by saving all key registers onto stock to preserve their values. The procedure clears the counter in CX, which will keep track of how many digits are in the number. Then, it sets up a loop to repeatedly divide the number by 10, isolating each digit from right to left. Each digit or remainder is pushed onto the stock, and the loop continues until the entire number has been processed. Next, another loop pops the digits in reverse order from left to right, adds the ASCII offset to convert them into characters, and prints them one by one. Once all digits are printed, the original register values are restored, and the procedure ends with return instruction. By running this program, this will show an output that the sum of all numbers in array is 1285. This is my fourth Java program, which is all about vowel and consonant counter. First, we have a return method for the vowels. Inside this method, the given word is converted to lowercase to ensure case consistency. Then, we loop through each character to check if it is a vowel. Each time the program finds a vowel, it increments the vowel counter. Also, we have the return method for the consonants. It also converts the given word to lowercase. It loops through each character, and if it is an alphabet letter that isn't a vowel, it counted as a consonant. In the main, I declare the given word, which is the pneumono ultramicroscopic silicovolcanoconiosis. Then there is an integer vowel to call the vowels method and store the result in vowel. Also, there is an integer consonant to call the consonant method and store the result in consonant. By that, the result will display the given word, which is the pneumono ultramicroscopic silicovolcanoconiosis, and then the number of vowels and the number of consonants. By running this code, this will give us the number of vowels count and the number of consonant count found in the given word, which is number of vowels is 20 and number of consonant is 25. This is the converted MO8086 assembly language of my fourth program. In this assembly program, we analyze a long English word, which is the pneumono ultramicroscopic silicovolcanoconiosis. First, we print a label and the word itself using DOS interrupt int 21H. Then, the procedure count letters is called. It loops through each character in the word, convert it to lowercase, and check whether it is a vowel or consonant. The check is done by comparing the character against a predefined list of vowels, which is the A, E, I, O, U. If a match is found, we increase the vowel counter. Otherwise, if the character is an alphabetic letter, we increase the consonant number. After finishing the loop, we print the results. The number of vowels and consonants are both displayed using a custom print decimal procedure. Now for the procedure, the count letters procedure scans through each character in the word using the SI register. For every character, it first checks for the string terminator to know when to stop. Then it calls the lowercase procedure to ensure the character is in lowercase for easier comparison. Next, it checks if the character is a valid letter, and if it is, it determines whether it is a vowel, and if it is a vowel, the vowel counter is incremented. If it is a consonant, the consonant counter goes up. Characters that aren't letters are skipped. The lowercase procedure simply checks if the character falls within the ASCII range for uppercase letters and converts it to lowercase by adding 32 or hexadecimal 20H. The if letter procedure checks whether the character in AL is a lowercase letter. It compares AL to the ASCII range from A to Z. If the character is in that range, it sets AL to 1 to indicate it's a letter. Otherwise, it sets AL to 0. The if vowel procedure determines whether a character is a vowel. It loads the address of the vowel list into DI, then loops through each character in the list. If it finds a match, it sets AL to 1. If it reached the end of the list marked by the string terminator without finding a match, it sets AL to 0. This allows the program to accurately detect vowels in the word. The print decimal procedure prints a number stored in AX as a sequence of decimal digits. First, it clears AH and sets BX to 10 to prepare for decimal division. It repeatedly divides AX by 10, storing each remainder on the stack. Each remainder represents a digit, and CX keeps track of how many digits there are. Once all digits are stored, the procedure pops each digit, convert it to its ASCII character by adding 0, and print it using interrupt 21H. This loop continues until all digits have been printed in the correct order. By running this program, it will show an output exactly like the Java program. This is my PIP program, which is all about reverse array. In this program, I start by declaring an unsorted array of 5 integers. I first display the original array using a simple for each loop. Then, I reverse the array in place. This is done by looping from the beginning of the array to the middle, swapping each element with its corresponding mirror element from the end. A temporary variable is used to hold values during the swap. Finally, the program prints the reverse array, again using a for each loop. This effectively flips the order of the elements without using any extra arrays. By running this code, we will have an original array of 34, 78, 90, 12, and 56. For the reverse array, this will be 56, 12, 90, 78, and 34. This is the converted MO8086 assembly language of my PIP program. This assembly program starts by printing the original array of 5 numbers. Each number is printed using a custom procedure, followed by a space for readability. The program then reverses the array in place by swapping values from the start and the end moving inward. Once the reversal is complete, it prints the updated array under the label reverse array. After reversing the array, the program enters a loop labeled print reverse. Each number is loaded into the AX register using the load SW instruction, then passed to the print number procedure. A space is printed between values for clarity using print space procedure. The print number procedure converts the numeric value into individual digits. It uses repeated division by 10, storing the remainders on the stack. Once all digits are stored, they are popped and printed in reverse order, giving the correct decimal output. Finally, the print space procedure simply prints a single space using DOS interrupt 21H, and the program ends with interrupt 21H function for CH, which cleanly exiting execution. Now, by running this code, we will have an exactly output like the Java program.